Thanks a lot for the invitation. It's always a pleasure to be, back in TIFR to give a talk, although this time it's virtually. So as Praveen said, my training has been in numerical methods for hyperbolic PDEs, but since then I've been exploring the world of scientific machine learning and trying to see how you can use machine learning tools to sort of overcome computational bottlenecks in classical numerical approaches. So today I will talk about one such application, and this is to do with, can we learn an optimal PD solution? Of course, the notion of optimal is going to be different for everyone, so I'll make that clear in a bit as to what I mean by an optimal PDE. And this work was done in collaboration with a bunch of people, as you can see on the screen, where the first person here is Philip Charles, and he is my graduate student who's been basically driving this research forward. And so let's get right into it. So here's the motivation. So PD-based problems are typically solved numerically using classical solvers such as finite difference, finite volume, element, spectral method, or any method that's your favorite. And of course, they have a robust mathematical theory. They work well in principle, give you very accurate solutions. Now, there are many applications which require the evaluation of this PD solver many times, sometimes of the order of 10 to the power 5 times. And examples include uncertainty quantification, data assimilation, PD constraint optimization, inverse problems, etc. Now, if in these applications, a single solve of this or evaluation of this PD solver is expensive, then doing these 10 to the power 5 solves of this PD solver can become almost prohibitively expensive. So that kind of brings about the need to design efficient and robust and at times differentiable surrogate solvers for the PD, which can give you these solutions very quickly and efficiently, but while also trying to build surrogate models which are consistent with the underlying PD theory. Okay, and that's what the talk today is all about. So in this talk, we will talk about this consistency with PD theory by trying to design something known as an operator network that can emulate the Petrov-Galerkin weak formulation associated with the PD. And the preprint for this is available on arXiv. There will be an update version that will be going up sometime this week. So if you want details of what I'm discussing today, and I won't be able to get into a lot of the details, you can have a look at this preprint. Okay, so here is the outline of my talk. I'll first describe what I mean by optimal PD solution and what kind of PDs we're talking about. I will then move into something known as the optimal Petrov-Galerkin formulation for PDEs. Then for those who have not seen neural networks before, I'll give you a very quick introduction to what neural networks are. Also kind of, introduce some important notations. And then I'll get to the main method of this talk, which is a Petrov-Galerkin variationally mimetic operator network, or PG-VarMiON for short, which is, I guess, the shortest name I could find. But it's an operator network that mimics this Petrov-Galerkin formulation. I'll talk about some error estimates that you can obtain using this PG-VarMiON. I'll then show you some simple numerical examples, and then end with some concluding remarks. Okay, so what do we mean by optimal? Okay, so for that, let's establish a kind of PD we are solving. So let's consider a generic elliptic PD operator, where L is our differential operator, and we assume that this differential operator is parameterized by some function G in some suitable function space. U is the solution that we're after. F is a forcing function, and keep things simple, I'm assuming homogeneous directly boundary condition. But of course, you can make this a little more general by also introducing a Neumann boundary condition, should you like it. So this is our generic PD setup. Of course, F, G, and U lie in the respective function spaces. U typically lies in some kind of a Sobolev space. And a typical example of say, a linear elliptic PD of this form is when we look at the operator associated with the 1D, or even not just necessarily 1D, it can be a higher dimensional steady advection-diffusion equation, where kappa over here is going to be a diffusion coefficient and C is going to be a velocity field. And this parameterizing function G will be a combination of the diffusion coefficient and the velocity field. So this is the operator that is parameterized by some function G. Okay, so we're looking at problems of this kind. And of course, we can then talk about not the strong form, but the weak form or the variational form of this PDE, where we are trying to find the solution U in some function space, again, typically a Sobolev space, such that we have the bilinear form on the right-hand side coming from the PDE operator. Again, the bilinear form is going to be linear in U and W, but parameterized by G. And on the right-hand side, we'll have the linear functional in terms of the source function F. And we need to satisfy this for every W in the same space. And under appropriate conditions on, say, this parameterization function G, you can talk about existence and uniqueness of the solution, which is guaranteed by Lax-Milgram. So I won't worry about the existence and uniqueness. I'll assume that I'm working in a setup where I have all the nice properties that guarantees that the solution does exist. Okay, and then I'll move forward from there and try to construct suitable numerical methods. Okay. Now, this over here is our infinite dimensional solution, because these are going to be infinite dimensional function spaces where U lies. But let's say we are trying to implement a method, and in doing so, we typically have to come down to a finite dimensional space. So here is now the setting. Let's assume we are given a finite dimensional space V bar, which is a subspace of V. And let's say we're also given a basis which spans this finite dimensional space, and I call those Pi. So there's an n-dimensional space where you have these basis functions, which I also call the trial basis, that's been given to you. And let's say what's also been given to you is an inner product, which I denote by a dagger notation. So this dagger inner product on V cross V is given to you. And of course, then you have the corresponding induced norm, which is also denoted by dagger. And the inner product or the norm will depend on the PDE being solved. It could be the L2, it could be some kind of a Sobolev norm that you'd like. So it's some norm that's been given to you, and you have been given this finite dimensional space. Now, let's consider the orthogonal projection P from V to V bar, which is defined that such that for any V in this space, whole infinite dimensional space V, P of V is simply the arg min of V minus W bar measured in this dagger norm, where W bar is a member of the space V bar, right? So you're trying to find the best, you're trying to find the orthogonal projection into this finite dimensional space, which is equivalently given by saying that the error between V and the projection is orthogonal to every element in this finite dimensional space, as measured in the dagger inner product, right? This is our orthogonal projection of any function into this finite dimensional space. And for this talk, we'll say that if U is our infinite dimensional, say, variational PDE solution, then the optimal solution will be P of U, which will be in this V bar space, right? So this is what I mean by optimal in this talk. And the goal would be, how do I recover this optimal solution or P of U without having access to U? Okay, so that's what we're trying to do in this talk. Is the setup clear? Any questions?
In a standard advection-diffusion equation, what would this mean, the optimal solution physically? Can you give an example?
In a standard, so all we are saying is, even a standard advection-diffusion equation, all you're saying is, you have the infinite dimensional solution, right? In whatever function space that you want. All I'm saying is I'm trying to find an approximation of the solution in a given finite dimensional space. And I'm trying to find the best possible approximation as given by a particular norm. That's all I mean. Okay, it's the approximation of the infinite dimensional solution in whatever basis that you want. That's it. I mean, if this was a finite element basis, then you're trying to find the finite element solution using the finite element basis, for instance. So that's what this is supposed to be.
Okay.
Does that answer your question?
Yes.
Yeah. Okay. All right. Okay. So moving on. So now let's come to this so-called optimal Petrov-Galerkin formulation, and let's see how this ties into this optimal solution. So we'll make an assumption over here, and this is an assumption about existence of something known as optimal weighting functions. So let's assume that for each of the trial basis functions that you've been given or you have chosen, so each phi, there exists a psi I in this function space V, such that this weak formulation holds, which is very similar to what we had earlier. But notice that the W and the psi, which we're trying to determine, has kind of flipped in order, right? So earlier we had A of U, where is it? A of U W, and we're trying to recover U. Now we have A of W psi I, where we're trying to recover the psi I. And on the right-hand side, we no longer have the F, but we have, essentially, we can treat psi I as the source term that is being defined in terms of this dagger inner product. So you can see this almost as the weak formulation for the adjoint PDE operator, where the right-hand side source is given by the trial basis. So let's assume that you can actually, for each phi, recover the corresponding psi I that satisfies this adjoint weak formulation. And if this dagger inner product was actually coercive in your original space, then you can use Rees representation theorem to guarantee the existence of each of these psi I's. And we'll call these psi I's, which will also be n of them, as optimal weighting functions. And we'll call the span of these optimal weighting functions as the V dagger space. Now, I will not necessarily claim that these psi I's will form a basis. Okay, they may not be all linearly independent, but I'll still look at these n functions, and I'll look at the dagger space, which is spanned by them. So I have the original space V, I have the space V bar that is spanned by the trial basis VI, and I have this new space V dagger, which is also finite dimensional, which is spanned by these optimal weighting functions. Okay, and this is what can now be used to find the optimal Petrov-Galerkin formulation, which is now saying that if we do have access to these weighting functions, then I want to find a U bar in this V bar space spanned by my trial basis, such that I have the same weak formulation that I originally had, but now the test functions are coming from this V dagger space, right? So instead of coming from the infinite dimensional space, the trial space is the V bar space, and the test space is the V dagger space. So this is, well, since the trial and the test spaces are different, it's called Petrov-Galerkin. But the question is, what is optimal about this? Okay, and the answer to that is actually pretty nice, because you can show without much effort that U bar is precisely the projection that you're trying to recover in this finite dimensional space. So U bar is exactly P of U, right? I may not get into the proof of it all. In fact, the proof, as you would see, is just 7 or 8 lines. But it's very easy to show that this is in fact the case, okay? And in fact, this and similar formulations have been investigated by a lot of people since the 1980s. And you know, there has been a lot of advantages of using this optimal Petrov-Galerkin formulation, especially over standard Galerkin formulations, which can fail in certain scenarios. But in order to use, so now we have a method to recover our optimal solution, right? The projected solution. We can just find the solution of this optimal Petrov-Galerkin formulation. This is a finite dimensional problem. But the issue here is, to be able to use this, we need to know what the psi I are explicitly. If I don't know what my weighting functions are, optimal weighting functions are, I cannot recover U bar, right? So this is the fundamental challenge with this optimal Petrov-Galerkin formulation. It's finite dimensional, it's nice, it's a very good formulation, but you need to know what the optimal weighting functions are. And recovering these optimal weighting functions can be challenging. Although for very simple 1D and 2D cases, we do know what they look like for a certain choice of the trial basis. In general, we don't know what they would look like. So you would need to solve n adjoint solves to recover the weighting functions. And since closed form expressions may not be available, you typically have to use another numerical solver, like finite element or isogeometric analysis, to actually recover accurately what these psi's are, then plug them into your Petrov-Galerkin solver, and then recover the U bar. So yeah, is that a question?
These weight functions, do you expect them to be like compactly supported?
They may or may not be. It'll actually depend on if the original basis phi's are compactly supported. If the original bases are not, there is no reason for these to be compactly supported.
Okay, so
In fact, I'll show you an example. Yeah.
the original bases are usual finite element bases, so they have compact support. So then,
Yeah.
this
So in
side,
this case, with this linear advection diffusion, you would find that they are also going to be compactly supported. Yes. They'll be compactly supported. In fact, in certain cases, you'll see, say, if we start with the hat basis functions for the trial space, you'll find that the optimal weighting functions are basically, slightly upwinded versions of the same thing.
okay.
So in certain cases with linearity and all, you can show that if you have compactness of the trial basis, then the weighting function will also be compact. But I'll show you an example here that if it's not, the trial basis is not compactly supported, then there's no reason why the weighting functions would be.
Can you go one slide back once? I have a
Yeah,
question. So, this basis phi were the basis for the whole infinite dimensional space.
exactly. That is what you or someone gave to you. So that's been predetermined. That's given to you.
So
PIs are the basis for the finite dimensional space.
finite where
Yeah.
we are projecting
Yeah.
into. So
Exactly.
can
So
you
PI is the
can you
fundamental space projecting it. Yeah.
so can you explain once more just how this trial basis is related to this? I didn't understand.
So trial basis is related to the weighting function you're saying?
No,
Or
how
related to
the
what?
CIs and the shy eyes are related, like.
Yeah, so it's related through this, right? So I'm saying that the optimal weighting functions, psi i's, right? They're a solution, they're solving this additional variational form or associated variational formulation where the phi i's are appearing as a source term on the right hand side. If you remember the original weak formulation, we had an F over there, right?
Yeah.
So now to recover these optimal weighting functions, you have to solve another associated variational form where your given trial basis is sitting on the right hand side as a source function.
What is the benefit of knowing that?
So that's helping me recover my psi I, right? So if I solve this, assume I can solve this, this gives me a psi I. Then using the psi I can try to I formulate this Petrov-Galerkin formulation, correct? Which is this one where U bar is in my trial space and W is in my this space spanned by the weighting functions. And the solution to this, this is a finite dimensional problem, the solution to this is exactly the optimal projected solution I was looking for.
Okay.
Right? And in this formulation, I don't need to know what the true solution U is.
Okay. Yeah.
Right? Make sense?
Yeah. No.
Okay. Any other questions? Okay. Yeah. So one challenge is, of course, you have to solve numerically n adjoint problems. Okay. Maybe that's not too bad. But the problem is we also have this parametrizing function G of the PD operator or of the bilinear form. Now, the psi i's depend on the choice of G.
So the G was
yeah,
coming from the PDE parameters, right? Only.
exactly. So in this case, it's basically, say, in linear advection diffusion, it's the diffusion coefficient and the velocity field. Those are going to be a G, forming a G.
So yeah, eventually you want to generalize over a certain class of parameters or something.
Yeah. So eventually, I'll get to that. I'll get to what I want to do. Yeah. So the whole point is that if my G changes, then I cannot reuse the same size because size depend on these optimal weighting functions depend on G. So I have to now solve n new adjoint problems each time my G changes. So now suddenly it becomes extremely expensive to use this optimal Petrov-Galerkin approach because each time my G is changing, I need a new n solves to get the optimal weighting functions. And it's because of reasons like this where the construction and recovery of the size was not easy. The optimal Petrov-Galerkin approach sort of diminished, whereas alternate strategies such as Galerkin least squares, residual free bubbles, VMS started gaining more popularity. So it sort of became less popular compared to other approaches.
So
what we want,
by any
yeah.
chance, the operator do you want to approximate should map G to this trial weighting functions.
Yes, G and the forcing function F, both,
Okay.
right?
So that you
Okay,
don't have the issue of changing G because now we approximated the operator.
precisely, right? Okay, so we want to revive this optimal Petrov-Galerkin formulation with deep operator learning, and I'll get to that in a bit, right? What I want to do. Okay, now before I get to any of that, get to deep learning, I'll talk about an alternate formulation of this Petrov-Galerkin formulation, which is actually a little more useful. So you can actually show that this optimal Petrov-Galerkin formulation that we have in the beginning, where you have the original bilinear form and you have the source function on the right hand side, is equivalent to this alternate formulation, where on the left you have now replaced the bilinear form by something that depends on the evaluation of the dagger inner product. So you have U bar phi I dagger is equal to F psi I, right? So there is no longer a bilinear form. In this case, the G is sort of disappeared. In fact, you don't even need to have explicit knowledge of the PDE operator to write this formulation. Implicitly, the knowledge of the PDE operator is embedded into the weighting functions. That's what possesses all the information. But if you use this form, you don't even need to know what the underlying PDE is. And it's a nice symmetric form on the right-hand side. You don't have a bilinear form, which might not be symmetric. So we will work with this alternate Petrov-Galerkin formulation. And this is going to be true for every single I going from 1 to n. And since U bar is in V bar, so it can be written as a linear combination of the trial basis, right? Where I say U bar I here is the coefficients of the trial basis. And I can write this in compact form as a vector U bar dotted with the vector of trial functions. This is going to be the representation of my U bar in this V bar space. Now, if I plug this into this alternate Petrov-Galerkin formulation, you will end up with the following, where I additionally assume that my trial basis is orthonormal with respect to this dagger inner product. And since you've been given the trial basis, since you've been given the dagger norm, you can always use something like Gram-Schmidt to orthonormalize them. That's not a problem. So we assume that the phi, phi j's are all orthonormal. If you do that, then you plug it into the PG formulation and you end up with the fact that the coefficient U bar that you want is simply given by this linear vector on the right hand side, where the ith component is simply the inner product of F with the trial weight, the optimal weighting function psi I. Okay, so U bar is simply given by this. You get this U bar coefficient, take the dot product with the trial basis, and you have your solution. But of course, the problem is that in this integral or the inner product, we don't know what the psi i's are a priori. You have to find some way of recovering them offline to be able to use this formulation. But this is the formulation, or this is the specific structure that the network that we design is going to try and emulate. So we're going to try to get something which looks like this in trying to recover the coefficients of the solution. And then you simply take the dot product with the basis functions, or the vector of basis vector of trial functions, and you're done, and that is going to be a solution approximation. Make sense? Questions at this point?
So F came from the PD, right?
F came from the PD. F is your source term. Yeah. Okay. All right. So as I promised, a quick overview of neural networks, if you have not seen this before. So a neural network in simple terms is nothing more than a parameterized mapping with the parameters theta, which is going from some input space to some output space. These are typically finite dimensional. And it's in its simplest form is given by an alternating composition of parameterized affine transformations followed by component-wise nonlinear activation of transformations. So what that would mean is say for kth composition, you will have a vector of size 4 going into it. You'll perform an affine transformation which requires a weight matrix W and a bias vector B. So you have a WX plus B. So you perform an affine transformation where W and B are going to be the parameters that I have determined. And let's say that gives you a 6-dimensional vector after you've done the transformation. Then you would take each component of this vector and you'll apply some nonlinear activation rho on it and that will give you an output vector of dimension 6. So this is typically what is happening at each level with an affine transformation followed by a nonlinear activation. And you have a series of these applying one after another till you finally end up with the output of the neural network in the space omega y. This is what the neural network looks like. And all these theta k's combined, which I will call theta, are known as the trainable weights and biases of the network, which is something you have to learn in some appropriate manner to achieve some goal, right? So it's just a parameterized mapping. And typically the way you would use a neural network is by saying that, let's say you have a relation f that takes x to y, but you don't know what f is. All you have is pairs of xi's and yi's, which are associated with the relation. What you want to do is you want to train a neural network so that if you give it an x, it'll try to give you a y, which is the same as the y that you would get if you were using the true unknown f. Okay, so you're trying to use a neural network, say, as a regression model to learn this underlying map f using the training data xi and yi. So this is how you would typically use a neural network. And to do that, you would need to define some kind of a metric that is helping you to figure out the discrepancy between, say, an x and y coming from the true data set and an x and the prediction coming from the neural network when you feed the x. So you want the different discrepancy between xy and the x and the prediction. And you would evaluate this, average this error over all, say, the training points, the data that's been given to you. This is going to be a function of these parameters theta, right? The weights and the biases. So then you have to solve an optimization problem, which tries to minimize this objective function. So this should not be psi, this should be theta. So you're trying to minimize this optimization function and find a theta star that minimizes this discrepancy over all your training points. And then with that theta star, the neural network n theta star is hopefully going to be a good approximation of your underlying function. So the way you should understand neural network is just a nonlinear regression model that is being fitted to learn on some data to learn some underlying function. That's all a neural network really is. You can come up with all kinds of fancy architectures as you would like, but the baseline, that's what a neural network is. It's just a nonlinear regression model if you're doing a regression problem. Of course, you have to find all kinds of hyperparameters. And for instance, how many layers do you want? How wide should the network be? What should be the activation function? How should you solve this optimization problem? What is the suitable loss function? In other words, what kind of metric should you use to measure the discrepancy? What should be your training data set and your validation data set? These are all hyperparameters. And most of your time when training a neural network is spent trying to determine these hyperparameters. But let's say that either you have the time or you have a student working with you who has the time to play around these parameters. You end up with a neural network that gives you a reasonably good approximation for functions, at least from a certain class at least a certain class of functions. So this is all a neural network really is. Before I proceed to how I'm going to use this neural network, any specific questions on neural networks itself? Okay, seeing none, I move on. So this is what a neural network is. But now I am trying to design something called as an operator network. So what does that mean for us? So we're talking about operator learning here. So let's say you have a function space f of functions on omega 1 and a function space u of functions on omega or some omega 2. So an operator S is nothing more than a mapping from function space 1 to the some function space 2, so from f to u. So that if I take any function f from this curly f and I feed it to the operator, I'll get another function in this function space u, right? So that'll be u of x, where x is now going to be sampled in omega 2. So this is what an operator is. It's just a mapping from one function space to another. So in the context of, say, our PDE, assuming, let's say, the G is fixed for now, then for our linear elliptic PDE, the solution operator of the PDE is the one that maps the f, the source function f, to the corresponding infinite dimensional weak solution u. If the G is also allowed to vary, the parameterization is allowed to vary, then it'll be an operator that maps f comma G to the corresponding solution u, right? So it's mapping functions to functions. So this is in the infinite dimensional setup. But then you can also talk about the solution operator for our projected solution, or the optimal Petrov-Galerkin solution, which says, well, given a forcing function f, I want to find the corresponding finite dimensional function u bar, which is our optimal projected solution, or is our optimal Petrov-Galerkin solution, right? And this is going to lie in the finite dimensional space spanned by my trial functions. So we want to design an operator network that tries to learn this particular operator, mapping f and possibly g to the corresponding finite dimensional solution u bar. Okay, is this clear? Okay, all right. So recall a few slides ago, we saw this the Petrov-Galerkin solution using an orthonormal trial basis, orthonormalized in our given dagger inner product. Since u bar can be written as a linear combination of the trial basis functions, or in compact notation, the vector u bar, vector of coefficients dotted with the vector of trial functions. And if you plug it into the alternate Petrov-Galerkin formulation, you get this equation for the coefficients u bar, where you have this vector on the right-hand side, which is linear in f and psi, and its ith component is nothing more but the inner product between f and the weighting function psi I, where the f is the source function that you're feeding as input. But the problem here was that we can use this provided we know what the size are, but we don't know what the size is supposed to be, which is why it's hard to use it. So this is what we will try to mimic. So we'll design our Petrov-Galerkin variationally mimetic operating network, or PG-VarMiON, using two ideas. First of all, we will replace this unknown trial basis vector, weighting function vector psi x, with a vector valued neural network, which I denote by psi hat, with parameters theta. So all this is doing is taking a vector. This is a neural network that takes as input x and throws out a vector valued output of size n, right? And I can treat each output as a corresponding approximation of the weighting functions psi I, right? So this is what I'm doing. I'm replacing the psi with the psi hat. And secondly, because you have to typically do this in practice, even if you have a classical approach, to approximate this f and psi I in a product, I replace that with a quadrature, which will lead to replacing this operator a, f of psi, with a quadrature-based approximation denoted by a sub h f and psi. Okay, so I've just replaced this by a quadrature-based approximation, and I've replaced the psi itself by a neural network. Okay, that's the only two changes I'm doing over here. Everything else remains as it is. The trial basis remains as it is. Nothing changes over there. Okay. Now, if I do this, we end up with an optimal Petrov-Galerkin formulation, and the emulation of the original optimal Petrov-Galerkin formulation is straightforward from this image. So instead of psi, we now have a psi hat, which depends on parameters theta. We again feed f over here into this block to calculate the coefficients of my expansion. The original coefficients are called u bar. My new coefficients are going to be called u hat. Okay, and here the a has been replaced by ah, and of course the psi has also been replaced by psi hat. Okay, so you have a quadrature approximation, and you have the psi replaced by psi hat. Then you use that to take a dot product with the trial basis to get the corresponding solution u hat instead of u bar. Okay, but the trial basis remains exactly the same as earlier. And of course, if your g parameterization g varies, then the g would also, well, the size will depend on g. So what we would do is this network psi hat will also be fed g as an input if the g actually varies in your problem. Okay, so the bottom is our PG-VarMiON, the top is our optimal Petrov-Galerkin formulation. Furthermore, because we know that we have linear dependence on f when I'm defining this operator a, right, which is just the inner product of f and psi I, typically by using a quadrature rule and using the psi, or this should be psi hat, this will actually take the form of a matrix A that depends on this network psi hat, acting on this vector f, where this vector f is going to be the evaluation of the source function f at the quadrature node. So you've picked a quadrature rule to define AH. This F is simply the discrete representation at this quadrature nodes, and that will be acted upon by a matrix A that depends in some specific way on the psi hat. Okay, so that's what this AH operator is supposed to be. Okay, so this gives me my coefficients. I take a dot product of this with the phi vector, and that gives me my PG-VarMiON solution.
So
Is this clear?
she hat is a matrix, right? Because there is a spatial discretization, I guess also.
No, so right now, in principle, it can be a matrix if I give you specific nodes. But the way I'm going to define this is I can evaluate psi hat at any point that I want, right? So at a given point, psi hat is a vector, correct?
Yeah.
Do you agree? Yeah. So then
Yeah.
I'm feeding the psi hat vector to A to value this A matrix, and then hitting it with F. Any other questions? So the important thing to remember here is I've embedded this very specific structure of what I want to do. I'm trying to mimic the optimal Petrov-Galerkin formulation. I've brought in a neural network only to determine these unknown psi's because I don't know how to evaluate them. Everything else remains the same, and just that the inner products are replaced by quadrature rules. That's it. That leads to this formulation of a vector of f's, a vector of a discrete vector f. That's about it. Now, the question is, how do you go around training something like this? Well, that's simple. Let's say you sample ND samples of Fj and Gj from their corresponding function spaces, do this independently. You use these to generate an exact or reference solution using another solver, say a finite element solver. So you have Uj, which is a solution when Fj is the source and Gj is the parameterization. Then you use this as your training set, and you define the training objective as basically being the mismatch as measured in the dagger norm that has been given to you between this true or reference solution and the solution that you would get with the PG-VarMiON when you feed the discrete version of F and G into the PG-VarMiON. And you take an average of that and you try to find the trainable parameters that minimize this loss. Of course, these are the parameters of my psi hat. So what I'm doing is I'm trying to find the parameters of psi hat, which minimizes this mismatch between the true solution and the prediction by the neural network. Now, the important thing to remember here is this is a supervised learning algorithm for U, because I do need the target or label Uj for each U hat J. But while training, I never need the exact or reference values of size. Okay, that is not known to me. But I'm still trying to recover the size by simply trying to minimize this mismatch. So it's an unsupervised learning for psi where I don't show what the true psi values are. I only show the true solution UJs, okay? And hopefully that will be enough to automatically and implicitly learn the weighting functions that give me something which is close to, say, a reference solution UJ.
But why not directly learn psi hat without, because it's possible.
Well, you could, but you can always ask, is there a benefit of also trying to learn the psi hats? The problem is then I have to solve an additional n adjoint problems for each new G. So even the training set generation can become more expensive, right? The way I would get the true size is by actually solving for the size by solving the n adjoint problems for every single G. You can do that. There's nothing wrong with that, but that becomes even more expensive. The question is, can I avoid solving for the size and directly learn it by just minimizing this? That will be a computationally simpler approach. Right. So maybe quickly telling you about some error estimates that exist, which tell you that this approach is good and can work. So just to remind us, U is the infinite dimensional weak solution of the PDE. U bar is a finite dimensional projection onto V bar, or the Petrov-Galerkin solution. And U hat is the PG-VarMiON solution, which will also be in V bar, because it's still, all we're doing is we're determining the coefficients of the same trial basis. So it's still going to be in V bar. So these are the three solutions that I have. Then something that you can show very easily is for any F, in fact, not just for any F, any G, you can show that the error in the dagger norm, the squared error in the dagger norm of U and U hat, which is the PG-VarMiON solution, the true infinite dimensional solution, can be exactly decomposed as the error between you and the projected solution, and the error between the projected solution and the PG-VarMiON solution, right? So we have this very nice decomposition. And in fact, this is telling us, even if we had the exact psi, right? If psi hat was exactly psi, we can never do any better than the projection error. The projection error is going to bound my error of the PG-VarMiON compared to the true infinite dimensional solution from below. So this will be the lower bound of my error, which means that if I give you a very poor choice of the trial basis that leads to very high projection errors, even the PG-VarMiON errors are going to be high. So it becomes imperative to select a suitable trial basis for the kind of problem that you're trying to solve. So you need some domain knowledge to be able to construct a reasonable trial basis. And this is going to be particularly important when solving something like advection-diffusion, because you'll have boundary layers, right? So this is the first error decomposition theorem. And then we have the, go ahead.
Is it, this is inequality or equality?
This is equality. This is strict equality. You don't need an equality here, which is the nice thing about it. And the reason why it's equality is because the U hat is also in the same V bar space. You can use that property in the fact that U bar is the optimal projected solution to get this equality.
Okay.
Again, details of this is in the preprint if you want to see how to obtain this, but it is an equality. Okay. And then we have the generalization error, which error estimate, which you at this point only have for a fixed G, where G doesn't vary. So you assume that G is fixed for your problem. Then what you can show is if F is any source function, then given any epsilon greater than 0, there exists a large enough training set, which is defined by a large enough number of training samples, ND, such that the error between you and the PG-VarMiON solution and this dagger norm is bounded by the projection error. This is something you've seen already, plus these remaining terms where you have the norm of the source function. You have these three terms where here's the epsilon you started off with. Epsilon t is your total training error, and this is something that you anyway track and monitor as you're training your network. This is the training error. Epsilon q is the quadrature error on the training set, because you're approximating your inner products with the quadrature rule. So epsilon q is the total quadrature error you're making on the training set. And of course, with the better and better quadrature rule, this can be made smaller. And the last term is, again, the quadrature error, but arising from the given f at which you're evaluating the solution. So if you have a good enough network which can make the epsilon training error small, we have a good enough quadrature rule, and you have enough training samples, you can actually get closer and closer to the true projection error, which is going to be a lower bound for the generalization error estimate. So this is at least a nice way of showing what are the contributing factors to the total error, and there are no hidden constants over here. It's a very nice interpretation of the various contributing factors. So at least it's important to have an error estimate like this to show that your method even makes sense and there is some hope of recovering a network that works. If you don't even have something like this, then there is absolutely no guarantees of even an existence of a network that can give you a good performance. But of course, this is what we have for generalization error. But let me convince you that the approach that I have works through some numerical experiments, okay? Because if the numerical experiments don't exist, then what is the point of this theory? Because it's not really a usable method. Okay, so let's look at 1D steady advection-diffusion equation. We have 0 Dirichlet conditions on the left and the right. So it's a simple 1D problem. Kappa is my diffusion coefficient. C is going to be a velocity field. Before I proceed, any questions about the error estimates, for instance?
Is there something about how you sample your training set?
That actually is hidden. Yeah. So this proof sort of is based on a very specific structure of F. So for instance, what does help is if you're able to, for instance, choose, the proof is sort of constructed on the fact that the training set is constructed as an orthogonal set of functions, okay? But you can also try to create a sampling which is done randomly from your space with some probability measure. But all of that will account to giving you some kind of a covering estimate, basically saying how well can you cover your function space F with the training set. So different ways of interpreting it, but the proof assumes that you are able to construct this in a nice, say, orthonormal manner. So it's almost like, say, a Fourier decomposition, right? So you're saying that you're able to capture, say, the first n Fourier modes or first Fourier n frequencies with the training set, and everything else can be bounded away if you have enough of these functions.
Okay.
Yeah. But of course, in practice, we won't do any of that. We will sample it independently and randomly from a distribution of the form that I'll show you. Okay, so we will look at a few methods to compare. First, of course, is our PG-VarMiON. So remember what the PG-VarMiON is U hat, where the solution is given as this coefficient, which is given by this matrix A that depends on psi hat, acting upon the vector F, which is a discrete realization of F. That gives you the coefficients, and you take the dot product with the given trial basis that is fixed, right, to get the solution. Okay, and this A has a very special structure that depends on the psi hat. It's not just any trainable matrix, but it's a very specialized kind of matrix that depends on a network psi hat, which is representing my unknown weighting functions. So this is PG-VarMiON. I'll talk about another deep operator network that is motivated by something known as depot nets. I'll call it an LDPO net because I'll assume that it looks similar to what I have earlier, okay? But the two differences, this A of psi hat is now simply replaced by a learnable matrix B, which has no special structure to it, okay? Because you could say, well, in principle, I can always write this A psi hat as some trainable matrix B. What if I just learn that matrix B and not assume any special structure given by the psi hat? Is that not enough? We'll see if it is or is not. And secondly, instead of fixing my trial basis as phi x, I'll assume that tau of x is another basis which is trainable. So you can train and find what these basis functions should be. So you're allowing flexibility in the trial basis, and you have removing the special structure of A psi hat. So that's what I'll call the LDPO net. The third one is what I call the B net, which is sort of between the PG-VarMiON and the LDPO net. Here, we'll take the same trial basis as the PG-VarMiON, and we'll simply say, is there any benefit of having the specialized structure matrix A? Can I not just have a simple learnable matrix B acting on the discrete F? Is that enough or is that not enough? So we look at these three kinds of operator networks. And for posterity's sake, I'll also have a fourth one, which is Fourier neural operators, which is another very popular operator learning framework, just to have a more thorough comparison with different kinds of frameworks, comparing how the PG-VarMiON works, okay? Any questions about these four frameworks? Or how they're related or different from each other?
Can you explain once more how the depot net differs from this PG-VarMiON?
So PG-VarMiON, I would say, if you know what a depot net is generally?
Yes.
Have you seen a depot net? Yeah. So depot net, you have tau is supposed to be the trunk functions, correct? The trunk.
Yes.
So you can treat phi as the trunk of the PG-VarMiON, but it's not trainable. It's fixed. There's no training involved. And the second thing is in the depot net, I'm saying that you just have a linear branch, which is with the learnable matrix B. But this B has no special structure to it. Every element of B is learnable or tunable. But in my case, it's a matrix A, which depends on psi hat. So it's not just any tunable matrix. It's a matrix whose components depends on another network psi hat. Okay? There's a very specific structure to this matrix over there. These are two differences.
Yeah. So it's like your network is like more problem motivated, like there is more structure to it. Yeah.
So you can say that I have some inductive bias in mind because I'm saying that, oh, I need a phi which is suitable to my problem, right? But a depot net says, why don't you go ahead and find what is suitable for my problem?
Yeah.
Yeah. Okay. But remember, they also have the B net, which I still give it the same good trial basis. But I'm saying, forget about the special structure on the matrix A. Learn any B. Can that work? Okay. All right. So I will, in this case, use my dagger norm as the L2 norm. Okay. And I'll assume that my velocity field C is positive or non-negative, which will typically create boundary layers on the right side. So we need to have a specialized trial basis that can accommodate for these boundary layers on the right-hand side. And we were able to use that to construct these 15 trial basis functions. As you will see, they'll all have this boundary layer-like feature on the right-hand side, okay? So these were almost, to some extent, handcrafted, designed for this particular problem. We do have a more general way of creating basis functions on more complicated problems, but this is the feed that has been given to me, which I'll work with for the PG-VarMiON, okay? All right, now the first problem is where C is fixed. C is non-negative, is non-zero, is positive, but it will not vary across samples. It's like saying that my parameterization G is fixed, it will not change. And I'll choose my kappa also as fixed, which is 10 to the minus 4. So it's the fixed configuration. This leads to a Peclier number of around 1,000. Now, the only thing that is varying for my problem is my forcing functions. And for training, I'll assume that the forcing functions are coming from a random sum of sine functions, as shown over here. This is the kind of Fs that we use to train on. And then we will test on 3 kinds of Fs. First, we'll take more Fs of the same kind that you saw in the training set. So it's in distribution F. But we look at 2 other data sets which have out of distribution Fs. In one case, F will come from a Gaussian random field with a length scale of 0.1, which is typically going to be less oscillatory than the Fs in the training set. So it's slightly simpler. And the data set 3 is coming from a Gaussian random field with length scale 0.05, which is going to be much more oscillatory than the Fs that you trained on. So we'll see if these networks are able to perform well in distribution F and also in out of distribution F, and what the performance looks like.
So have you tried, in case like your 10 was fixed, right? Have you, while testing, have you varied?
The 10 over here?
Yeah.
Yeah, so this is something we picked. We haven't looked at a lot of variations of this. What we found is by taking a sum of sine functions, let's say 10 was enough for training for this problem. Again, you could say what happens if you have less of these, more of these. That's a hyperparameter tuning question at the end of the day.
No, I'm asking, once you have trained, now you're testing. So
Yeah.
while testing, you kept the same form for this function and changed the distributions of ages and b's.
Yeah. No,
So
we haven't done that. So
have you
no, so we
changed
haven't.
the 10 while testing?
The 10, no, we haven't,
Okay.
because otherwise that will make it out of distribution. So the in distribution is the same kind of function formulation, but different samples of ages and bj's, of course, right? But the OOD does not look like this at all. It's this Gaussian random fields. It's
I
not
see.
sum of sine functions at all, right?
So that will have
Okay.
much more number of modes were decaying, maybe, depending on what
Precisely.
you're.
Precisely. Exactly. Depending on the length scale. Exactly. Right. Okay. So just to show you what the PG-VarMiON look like, the error on these 3 test sets look like compared to the actual projected solution if we compute it offline. So you see these are the histograms. So here the blue is the projected error, and well, it's not VarMiON PG, it should be PG-VarMiON. This is the older name. And that's the histogram of the test errors for the PG-VarMiON on dataset 1, dataset 2, and dataset 3. And here I'm showing the RUG plot to show how these errors are kind of distributed, the relative L2 errors. And we see that at least on average, we are not too far from the projected error, right? And remember, we cannot beat the projection error. That's our lower bound. We seem to be doing well here in terms of getting close to it. But what about the other methods? How did they perform on this data set? Well, before that, let me show you what the performance on data set 3, which I said was the hardest out of distribution data set is. So this is for the PG-VarMiON, 4 different Fs, test Fs. And in the bottom, you see the solutions where the red dashed curve is the reference solution and the triangles is the PG-VarMiON solution. So at least I guess in the eyeball norm, they look indistinguishable. So you're actually capturing that and you're capturing this boundary layer quite accurately. That to some extent is because you have that built into your trial basis.
You meant boxes,
and this
right?
is what,
Not triangles, I guess.
Not triangles, yeah, boxes, yeah.
Yeah.
Apologies for that, yeah, boxes, yeah. And then this is, for instance, what the errors look like for different methods on dataset 1, 2, and 3. What you would find generally is this is where PG-VarMiON is. It's comparable to FNO. FNO is supposed to be a really good method on most of these data sets. L DeepONet, the error is much larger. In fact, it's significantly larger on this out of distribution data set 3. And the BNet actually performs well on the data set 1 and 2, but it gives you the largest error on data set 3. And this is perhaps because you're overfitting the data by not having the specialized structure of this matrix A and replacing it with B. So it works well on simple or in distribution data, but out of distribution data, it just goes out of the water. And of course, you can do the same kind of analysis by saying, varying the number of training samples you have, instead of using 4,000 samples, what if you only had 100 samples to train on? And we generally find that the blue curve, which is our PG-VarMiON, seems to be robust across all 3 setups. I will speed through now because I know I'm running out of time. So the main question is, I've done all of this, but remember, I have a network that is trying to learn the true size, right? The weighting functions. Do I actually learn those at all? So this is an example. The dashed curve here is the true size, which are computed offline by solving the adjoint problems. The red curves are what the PG-VarMiON has learned. So maybe barring the last 3 high frequency modes, the PG-VarMiON is able to actually recover the underlying trial basis functions in an unsupervised manner without being shown the true psi, okay? So the PG-VarMiON is able to learn this, and which is why it's able to perform well on out of distribution F as well, because you've actually learned the solution operator structure of the PDE in this Petrov-Galerkin formulation. This is what gives us good performance. I will now show you what happens if you vary C as well, and I'll end with those results. So what if now kappa is fixed, but C is spatially varying given by a tan H function, but the tan H function is sort of shifted left and right, and the steepness, the sharpness of this transition region can also be varied. So we have different kinds of Cs. So this is now going to be fed as a discrete input to my psi hat network, because the psi hat should depend on these Cs. The fees will be exactly as earlier, so the same trial basis, the same kind of training F as earlier. And then we'll try to see what happens once you train it. Does it perform well on test data? So this is a comparison on the same 3 kinds of test out of distribution and distribution test data. Again, if you notice, the projected solution and the PG-VarMiON solutions are relatively close to each other. So we do well in distribution and also out of distribution. And if you look at the hardest data set 3, with the F and the corresponding C, we see that our solution matches the projection and the PG-VarMiON solution quite well. Our solution is given in this blue star. So we're doing quite well in approximating the reference or the projected solution. And the golden question is, are we still able to learn the size as my C is varying? So for example, this is for one particular test samples, this is what the size look like. The black dashed curve is the reference size. The red one is what we are learning. Now with the same trained PG-VarMiON, I'll give it a new velocity field, is able to adapt and change the weighting functions. So this is sample 2, and this is sample 3. So as my C is varying, my underlying trial, the weighting functions are changing, and the PG-VarMiON has learned how to adapt and change the learned psi hats as well to the varying velocity field, and hence is able to perform well even on outer distribution samples. So I know I've reached my mark, so I'll just show you the concluding remarks, and I will stop here for further questions, if there are any.
So your network looks like more similar to DeepONet, I think. Than the
In a way, so in a way, it has similar flavors to the DeepONet, right? But the difference between this and the DeepONet is, in the DeepONet, you're training for the trunk.
Yeah,
We are
but
not, right?
that is true. But when you train the Fourier neural operator, you just gave the forcing functions ng and directly the solution, right?
Yeah, so we haven't yet trained a forcing function for the varying G case, but at least for the fixed G case, you just give it the full field of F and just learn the U, right? And
Like,
FNO, of course, does not have the same structure as the DeepONet. It's very different.
yeah, like your network, I can visualize like how it is like set up for the problem, but like any idea why the FNO also perform well? Like,
so the FNO is known to actually perform well because of it has this FFT form position. It's trying to build in. There's a lot of there is papers that link it to kernel learning. You're able to learn the let's say the what we could the you're able to somehow learn the Green's function of the operator. There are papers that talk about that. But even with the FNO, the thing to remember, and this has always been noticed by other people, the FNO sort of works well assuming you have enough training data, right? In this case, when I had say just 100 or 500 training samples, you see how large the FNO error in orange is. It's much higher. So the FNO actually is known to perform well, subject to you having enough training samples.
Okay.
Otherwise, it can fail.
Okay.
And it is typically more tedious to train an FNO because there's a lot more happening in there with the FFTs and the inverse FFTs.
Yes. Yes.
So you had to choose, you chose some type of trial functions phi, which in practice we cannot do that, right? What happens?
Precisely.
We use, suppose I just use standard triangular hat function. Why don't you just use them?
So we could use the hat.
The size should still learn about the boundary layer themselves, right? Even if you have hat functions.
Sure. In fact, we did one step more. We said, okay, what if we just replace it by the sine functions of different frequencies, right? We tried that. The problem with that is if I look at just the projection error, not even bringing the network into picture, what is the projection error? We needed about 200 sine functions of increasing frequency to bring the projection error to something like 3%, right? So you need a much larger basis to do essentially to try to learn what's happening with the boundary layer on the right-hand side. And at those, at that level, it becomes computationally difficult to even train a network. You can do it, but you need many, many more basis functions compared to something which is more customized. What we have also tried, and of course, this is not an extendable approach. What you could try to do, and this we found works quite well in practice, is you have your training set. You could say, well, I will choose a spline basis, right, a B-spline basis, and I'll try to find a B-spline basis just on using the training data or a subset of the training data that minimizes my projection error. And you pick that as your phi and you move on. And that's a very simple problem to solve. It's not very hard to train and find these phi's. You can use those phi's and work with them. And they're able to capture features such as boundary layers quite accurately. In fact, we have a 2D problem that will appear in an updated manuscript very soon. We use that approach and it works quite well.
So when we solve with a classical method, so when you make a grid, you will obviously have a clustered grid in the boundary layer. So suppose I make such a grid and take the hat functions corresponding to that. It should work well, no?
Yeah, it should work well, and that works. So in this 1D case, I completely agree. You could have had a clustering of nodes there, and you could have had concentrated hat functions sitting there, and that would have also worked because you can choose whatever quadration nodes or whatever discretization you want, right? And that in principle could work. Even if you do the challenges now, if you go to say a 2D setting where you don't have a constant velocity field, say you have like a vortex which is sitting near the boundary. You have parts of the boundary which is going to have a boundary layer and other parts which are not. In that case, while you could still do clustering, you could do something better that can also work for a scenario when the vortex structure is moving. For instance, the vortex is sitting completely inside your domain. There will be no boundary layers. It's only going to have boundary layers when it's at the boundary. So you don't want to waste a lot of cells at the boundary in certain scenarios when there will be no boundary layer. But you can build in additional customizations of the form that we talked about into the setting. You could have considered a discretization of f and of the other functions which have this clustering near the boundary, and you could have chosen corresponding trial basis concentrated at the boundary. I don't see why that can't work. That would have also worked. The point is, you can bring in any level of customization to this as you want for a particular problem. But even if you do that, you still have to, of course, find the corresponding weighting functions, but you can find that using this approach once you've given it a good trial basis. So it's up to the user to come up with a good construction for the trial basis.
Okay, and what about say something like Navier-Stokes and time-dependent problems, such things?
Yeah, in fact, that's one of the challenges, because this is something that we have first got started, because you could ask, why am I even doing this? You have other methods that can solve complicated nonlinear time-dependent problems. The whole goal is we are trying to rebuild this operator network structure in the way that FEM, for instance, was built, right? From starting from the variational form and try to come up with structure that makes sense. So we're slowly building out. So we are next going to try to see if we can do time-dependent problems over here, maybe keeping it still a linear in space, or then slowly bring in non-linearities in the PDEs, then perhaps bring in things like varying geometry. So one by one, we're kind of moving upwards, trying to bring in these complications or complexities into the formulation, which is still consistent mathematically, and then trying to see how it performs. But the goal is to hopefully be able to solve something like Navier-Stokes eventually on 2D or 3D domains.
Any other question?
Yes. Thank you for your presentation. The DAG norm you use here is L2. Is it enough? Why not go to, let's say, L1 norm, H1 norm?
You can, and in fact, that's something that we've been trying out. In fact, the H1 norm, it'll be nice because then you also have things like reversibility. So things are guaranteed automatically, right? So H1 is a nicer norm. It'll help you control even the derivatives of your solution quite nicely. In practice, what we find is when you're training with something like H1, while your gradient approximations become significantly better, you do lose accuracy in the L2 sense, right? So there's a certain balance that one has to maintain there in practice. And of course, on theory, you can choose whatever you like. In practice, there's a little more required to sort of make sure that you don't deteriorate significantly the L2 approximations in trying to control the gradient information.
And the ratio between the convection and the diffusion need to be some, let's say, you are Péclet of Péclet of 1000.
1000 there.
Yeah. Okay.
Yeah.
Okay.
So it's a scenario where standard Galerkin approximation, unless you use something like SUPG, is going to give you tons of oscillations near the boundary layer.
Okay. Thank you.
In fact, even to generate the reference solutions here, we did use something like SUPG to generate the reference solution. Otherwise, it's useless.
Okay. Thank you.
So another thing, when you train this network from the number of parameters I saw for the specific problem you showed, it was not very complex, right? To train it, it was fast.
No, it's
very fast.
it's relatively fast. I mean, I think these take for 1D take 4 minutes to train.
Yeah. For which GPU did you use? You used a GPU?
I think we use A100s.
Oh, then it will happen in
A100.
just in a blink of an eye.
Yeah, exactly. But of course, when you go to 2D, it becomes something like 40,000. It becomes much more complex.
So the thing is regarding complex, so did you forget just finding out the trial basis for now, like the initial fee basis? So
right.
After you design the network, so it can find solutions in, I guess, seconds, because you don't have to go through numerically solving at all.
Sure. Yeah.
So,
which is essentially the whole reason, the primary motivation that you want design surrogate models that can give you solutions very quickly. In fact, an application that we have done is we have used this into an inverse problem setting, where this surrogate model sits there to kind of ensure physical consistency.
so
but you can do this very quickly with exception. Yeah.
So in case the initial that fee basis is finding that fee basis is complex, do you have like a specific algorithm which can find it in certain amount of time, the initial basis, because that also adds up to the how.
Sure. So we do right now have a B-splines based algorithm that can actually do it very efficiently, even for 2D problems. It's not
For
problematic at
elliptic
all.
problems, like 2D problems.
2D problems, yeah. For 2D problems, I mean, honestly, to find this, I mean, you can say it's an elliptic problem. You can say it's not an elliptic problem. At the end, what you'll use is you'll use a set of say, solutions sitting in your training set, right? And you'll use that to sort of minimize projection error.
And the number of parameters, I guess, is proportional to the number of that basis functions are there, right?
Number of parameters in what? In the psi, you're saying, or in the phi?
In the psi, like if the number of phi increases, I guess.
Yeah, of course. I mean, if you have more phi, then you'll need as many psi, right? But of course, it will scale linearly in the number of
it will scale
trial space
linearly.
functions. Yeah, but of course, what will also scale in, and that will be non-linear, is how complex each psi is, right? If it's really oscillatory, it might lead to very oscillatory psi as well. If phi is oscillatory, psi will be oscillatory, which means you need a expressive enough network to capture those features.
So you didn't try it still now for non-linearity and non-linear problems, right?
No, we are moving towards that slowly. So right now, if you think about it, as soon as you start varying G, the solution operator is nonlinear in G.
Yes.
Right? It's linear F and nonlinear in G. Of course, I guess what you're asking about is what is the operator on the solution is nonlinear. We haven't gone to that yet. No.
So another thing, so look, just asking, like, if you're thinking to move into time-dependent problems, so then there is the thing is like given an initial condition, you want to eventually step by step, right? So how will you formulate the operator in that case?
Well, I said we're still in the process of figuring that out, but we are looking at more of an auto-regressive kind of formulation there, right? You're saying that the output at one time step is going to fed into the next one.
So basically in this way you're thinking, right, that the operator takes dt as a function also, like it moves dt at a time, like given the solution at a certain time, it moves by dt also.
Yeah.
Then you mentioned auto-regressive.
Exactly. So you would say maybe if you're able to learn the operator network will be like a time stepper for you. That's what you're learning.
Yeah. FNOs are basically used a lot in that way, I guess.
Precisely. FNOs can be used. There are also DeepONet ways models exist which can do that. So my point is these things have been tried. We're going to try to bring it in, but of course it's not just about doing that. We want to see how do we relate it back to the variational form, right?
Exactly. That is what my question was going to be. So how will this method combine with any ideas, like just asking?
Well, I would say just wait, hopefully wait for a couple of more months and you'll find something that will be put out there. We don't have a concrete answer yet. We're looking into, well, A, what makes sense theoretically, and B, what can actually work well in practice. That's the combination of both.
Okay.
Okay, so we can formally close the session, but